Hello everyone, so today in this video we will be looking to calculate and plot the pressure volume isotherms of water using Sauve-Redlich-Kwong method. So to deal with these problems, we first open our collaboratory and import all the tools that we usually need to solve such kind of problems. So we need the CHE tools and NumPy, SciPy optimize and plotlight to graph our plot. So we import that. So before we start the plotting, if we look at our generic cubic equation of state, we have our parameters of B, A, epsilon, and sigma, right? So let's just start our calculation by defining a function that would determine us the values of B, A, and epsilon and sigma. So we'll just before that, let's just import the properties of water from SHE tools as P props of water. Let's just run it. It says no GPU found because the program is specialized to work on GPU, so we'll be using CPU instead. So let's just define function now. So let's say it'll be called like cubic AB, like AB value, like epsilon and sigma, just AS, right? Okay. So we have some our equations for calculating beta A value, and our epsilon and sigma values are already given, so we will be using SRK method. So this line here represents the values we will need. So let's just start by getting that. So our value for sigma is gonna be equal to 1, right? And our value for epsilon is gonna be equal to 0. And our value for omega, we will also need it like while calculating other parameters, is gonna be equal to 0.08664. And our value for psi, the sign is called like this, is gonna be 0.42748. And now we will have to define our A. So if we look at our equation of A, we need here this value, which is temperature reduced. So the temperature reduced is our actual temperature divided by the critical temperature. So we'll just define it like temperature reduced is equal to the temperature over temperature critical. So we get that value from our CHE tools. So here we see we need the temperature value. So our function would get the temperature as an input. Sorry. Okay. So we are done with T reduced. So let's just write the equation to find A. So it's going to be equal to psi multiplied like psi multiplied by alpha. So we need the value for alpha, right? So if we look at that, this is going to be our alpha, which is this value. So we will need to define our alpha first before defining our A. So our alpha would equal to the value. So in order not to miss with the square, right, we have a very long equation. Let's just write the square first and write everything else inside. So it's going to be 1 plus 0.48 plus 1.574 multiplied by PV. So this is the omega value. Sorry, this is the like this value here. So and minus 0.176 multiplied by here's so this is the V value for specific value for water, and we have squared, and here we'll multiply this by 1 minus temperature reduced, right, to the power of 0.5, right? And so now we can write an equation for our A value, which is going to be equal, like, if we look at this, it's going to be so psi, so in this value, so it's going to be psi alpha multiplied by, it's going to be alpha multiplied by r squared, right? We already defined our r at the beginning here as it's a constant, and multiplied by temperature critical squared, so it's going to be temperature critical um, temperature critical squared, right, and divided by pressure critical. So we're going to get all these values from our CHE tools. Pressure critical, right? Pressure critical. Okay, so we already write down our equation for alpha. Now let's move on to B. So if we look down here, like here we can see the equation for our beta from the day, like from the textbook. So it's gonna be omega multiplied by R multiplied by critical temperature divided by pressure critical, right? So now we have, as our function was determined, like was specialized to output our A, B, E, S values. So like A, B, epsilon, and sigma values. We'll just say it's gonna return A, B, E, epsilon, and sigma values. So let's just run. So we don't have any errors here. So now let's, as we want to plot our generic cubic equation of state, let's just define another function that would calculate our cubic pressure, right? So we'll say this, it'll be cubic P, right? So it's gonna take the value for temperature, like it's gonna take some kind of uh, matrix, and it's gonna get the value for temperature. And let's just unpack our B. It's gonna be epsilon and sigma, right? Um, it's gonna be cubic, cubic, oh, cubic, maybe yes, right? G. Okay. So here this value is gonna be our volume. Like as we have volume here. So this like generic cubic equation of state is dependent only to the temperature and volume that are going to be our inputs, and all the other variables, R is a constant, and A, B, epsilon, and sigma are parameters parameters which we already determined. So we're missing column here, right? So let's just here says okay, let's just write our equation now. It must be tab, right? Okay. So our pressure, like cubic pressure, is gonna be equal to RT divided by V minus B, which is a excluded volume of a molecule, minus, right? So we're gonna have A divided by, it's gonna be equal to volume, volume plus epsilon multiplied by B multiplied by volume plus sigma multiplied by beta, right? So this is going to be our value that our function, this is going to be the value our function returns, which is the cubic pressure. So we'll just run that. Okay, so now let's just move on into the plotting stage. So our plot, like the axis of our plot, will be dependent to our value of B, like B, which is the excluded volume, right? So as we are using the SRK method, let's just write our B again here. It's gonna be this value. And our omega was 0.068664, right? So then we're gonna have to give some values for our volume, right? So we can use numpy linspace for that. However, if we plot our graph with using the linspace, it's gonna give us a value with the that is not real like that doesn't look like our plot. So usually for plotting very like a lot of data, we use the NP log space because the distance between the values are pretty big. And so we're gonna have to input our so this would take our NP log base 10. So our the starting point must be a bit bigger than the B value. So it's gonna be like 1% higher of the B value. And let's just say -2 here, like for the where we want to end, and 500 points. And so we will need our fake. So we'll not need to have a figure. So let's just fig equals, we know, like make subplots, right? Okay. So let's just graph the plot the value for only one temperature. So let's say we're gonna have the temperature equal to 400, right? Okay. What are you gonna say, like figure dot add scatter, right? So for our x value, we're gonna have our volumes, and for our y value, we're gonna have our pressure values, right? So here we define our cubic pressure. So let's just unplug it first. Like you will say, it's gonna be equal to our pressure, cubic pressure, right? So it's gonna take the volume and the temperature. So our value would be the variable P. and we'll have mode lines. Oh, might be equal lines, and so let's just try to plot it. You see, the mistake here we made is we need only this graph is too big, so we need only this part, and we have to make our x-axis in a log base because we are getting the like log space for our v, right? So we're gonna say like figure dot update. So let's just make our x-axis like logarithmic, right? So x-axis axis. So type is going to be equal to log, right? And let's just give a boundary for our like graph because it's like too big. So as we can see here, it definitely goes below 0. So we can give value of 200 millions for our starting point. So like figure update y-axis. So we'll start like range from, so let's start by negative 200 millions, right? As we definitely know that it doesn't go until that, so 200 multiplied by 10 raised to the power 6. And here, let's go to positive 200, right? So let's just, wait. Okay, figure object has no attribute y-axis. Oh, here there's a typo. There is an X, so we should have had S. So this is our graph. So this is the plot of our generic cubic equation of state for the temperature of 400. So now let's just try to plot our like cubic equation of state for temperatures starting from like 275, which is greater than K, like 1 Kelvin, until 800, right? Like 775, let's say that's going to be our last value. So we don't need this value anymore. We're going to have to create a um, so repetition, like repetition loop. So we're going to say for t in range. So let's say we said like we're gonna start from 775, so which is greater than 1 Kelvin. Let's uh let's say it's gonna be 800, so our final value is gonna be 775. So let's say like if we say it's 25, it's gonna be 775, right? So 25 is gonna be our like ranges between different temperature. So we're gonna need to indent it, indent, indent. Um, Actually, we don't really need to indent, like, because it would apply to our plot. So let's just add our, like, a name for our plots so that we can differentiate between them. So let's say name is going to be equal, so we'll use this f string. So in this case, we can say that our t value is going to be equal to the variable, which is t, right? So it's going to change as we have a loop, which has a unit of k. So let's just check our plot. I see here we made a mistake here. We should have had our p equals here inside of this because it should calculate our pressure value every time in the loop, right? So let's just run it. Here we go. This is our plot for generic cubic equation of state of like water for the temperature starting from 275 until 775. And our critical point, which is like when the slope of the graph is equal to 0, is going to be somewhere between this. So this was the video for plotting our generic equation of state, like pressure volume isotherm of water. And thanks for your attention.